In the previous episode, Planck introduced the first quantum. Energy no longer appeared perfectly continuous, but physics still believed one thing with confidence: that light was a wave. And then came the experiment that changed everything. Wave behavior seemed undeniable: interference, diffraction, propagation. Everything pointed toward light being a wave. Then physicists discovered something strange. When light strikes certain metals, electrons can be emitted. This became known as the photoelectric effect. Classical wave theory predicted something simple. If light carries energy as a wave, then brighter light should eventually eject electrons. More intensity should mean more energy. But reality behaved differently. Sometimes extremely bright light produced nothing. No electrons, nothing happened. And sometimes weak light immediately ejected electrons. This was deeply disturbing. The crucial factor was not brightness, it was frequency. And this changed everything. Intensity measures how strong or bright a wave is. Classical physics expected higher intensity to deliver more energy, but nature disagreed. If the frequency was too low, no electrons emerged, no matter how intense the light became. Albert Einstein proposed a radical idea. What if light is not only a wave? What if light also behaves like a particle? Einstein proposed that light arrives in discrete packets. These packets became known as photons. A photon is the quantum of light. This changed the meaning of interaction itself. In a wave picture, energy spreads continuously. But in the photon picture, energy arrives locally. One photon, one interaction. Einstein used Planck's formula directly. Each photon carries energy equal to h times frequency. Higher frequency means higher photon energy. Low-frequency photons may not carry enough energy to free an electron, no matter how many arrive. And suddenly the experiment made sense. Frequency determined whether a photon carried enough energy, not brightness alone. This was catastrophic for classical physics. Light behaved like a wave during propagation, but like a particle during interaction. So what is light? A wave, a particle, both? A wave is spread out, a pattern distributed across space. A particle is localized, a discrete interaction event. But light appeared to possess both behaviors, and classical reality had no category capable of describing this. This became known as wave-particle duality. The same system could behave differently depending on interaction. Reality itself appeared context-dependent. And now a deeper question began approaching physics. What exactly is light before measurement? A wave, a particle, or something beyond classical categories entirely? This experiment changed quantum theory forever. Quantum mechanics was no longer only mathematics. Reality itself was behaving differently. Einstein did not receive the Nobel Prize for relativity. He received it primarily for explaining the photoelectric effect. Because this experiment proved that quantum ideas were physically real. Classical physics treated reality as fixed categories: wave, particle, object. But quantum mechanics began dissolving those boundaries. Light no longer behaved like a stable classical object. It behaved differently depending on how reality interacted with it, and quantum mechanics had only just begun. The photoelectric effect revealed something terrifying. Reality may not obey the categories the human mind evolved to understand. In the next episode, quantum mechanics will become even stranger, because light will not be the only thing behaving like a wave. Matter itself will begin dissolving into probability.